natural convection. So natural convection is let's see what natural convection is. So natural convection is the combined heat transfer by conduction and advection, as is always the case of convection. But in this case, the advection is not due to an externally imposed velocity, but instead to differences in buoyancy. So, for example, in a pipe, we're forcing the flow down the pipe. That's why we have pumps. That's forced convection, internal. In the case of, for example, the wind blowing on a building that was heated by the sun, the wind is imposing a velocity of the air that takes the heat away. Now, sometimes we might have no externally imposed velocity. For example, we might be heating up a building, but there's no wind. Or the case for those of us in MADI, when we talk about normalization, you get a red hot piece of steel out of the furnace and you leave it sitting there in the shop to cool down. How does it cool down? Nobody's blowing air on it. That's the point of normalization, right? But we would see the hot air rising. When we are in a bonfire and we see all this turbulence above the fire, that is due to the natural convection of the air that is rising because it's lighter when it's hotter. So we see so many cases. Cool things that we will explain based on natural convection is something like you might have seen a few weeks ago. I took this photo myself a few years ago. This is in the middle of the winter. This is my kitchen window, and it's frosted at the bottom. And it always starts freezing at the bottom. Why? I'm sure you have your thoughts and you have your theories. But if you pay attention, it's super interesting. Why does it freeze at the bottom? We will explain that, and the explanation is based on natural convection. I have a video here that I think is going to be cool to illustrate some aspects of natural convection. Typically, natural convection is due to differences in buoyancy because of temperature. And that's the only case we're gonna study in this class. However, we can have natural convection due to differences in density because of mass transfer. For example, salty water is heavier than pure water. So as the salt dissolves, the densities are changing, and we would see fluid flow that is not induced, that has natural convection, but in this case has nothing to do with the heat transfer and everything to do with mass transfer. Let me show you a video to finish the day that involves that involves natural convection experiments due to temperature. I hope you don't get this sound because it's terrible. Okay. So in this case, they're putting water in a beaker and they're gonna heat up the water, and they put dye in the water, so we see the flow right into the clean water. So what he has in the beaker is hot water that is dyed with red ink. Okay, there he's heating it up. He doesn't mean to boil it. He just wanted to be hot, because hot water has lower density than cold water. And he puts it into the cold water. Isn't it cool? Now the hot water is rising. Much like a chimney in an industrial operation. There is no pump in this case. It's pretty amazing that we are getting mechanical energy out of kind of nothing, right? It's just a difference in density. So he puts ice, it cools down the water, and it falls down. So you get to see that there, in the end, there is a velocity. And we said that our calculations of convection are all about getting the thickness of a boundary layer, right? If I know the thickness of my thermal boundary layer, I know my heat transfer by convection. Now, when we have an external imposed velocity, we learn how to calculate the boundary layer thickness. In the case of natural convection, nobody's telling us what the external velocity is. The whole trick here is going to be figuring out what the external velocity is to calculate a boundary layer, right? So we're going to see new dimensionless groups other than Reynolds and Prandtl. So here is an interesting example. He talks about the tectonic plates. The Earth is a huge convective flow in which the hot flows, the hot material from inside the Earth is flowing. Not only are parts that are kind of liquidy, over the millions of years, the solids flow pretty much like a viscous liquid too, right? And much of what we see in our Earth and earthquakes and all those things are due to these natural convection currents that happens not in seconds, but in millions of years. I think it's pretty amazing. Here you go. He calls it tectonic plates. So before we close, what are we going to see? We're going to distinguish laminar flows from turbulent flows. The catch is we don't have an external velocity, therefore we cannot calculate a Reynolds number easily. So we'll have another number that is kind of somewhat plays the role of Reynolds, but doesn't involve a velocity, right? We are going to then see a bunch of correlations, most of them empirical. And this is very similar to what we have seen for convection so far. We're going to see plates and cylinders and spheres for external flows. We're going to see natural convection in internal flows too. And then we're going to see something that we hadn't seen in so far. That is enclosures, that is recirculating flows, right? And then at the end, that will be next week, we're going to see what happens when we have both an imposed velocity and natural convection at the same time. So I think our time is up for today. I'm going to take a 10-minute break and be back at 2 for office hours. And before we break off, I will close the anonymous survey over the weekend. If any of you still would like to share thoughts or suggestions for improvement with me, please go to Socrative. I'll close it over the weekend. So I hope you can do it. Thank you very much. I'll see you at the office hours, or I'll see you on Monday. Thanks.